So in this video, I just want to really hammer home that point about using square root substitutions and why they work even though it's not an invertible function. The short answer is it works because of properties of polynomials and the algebra we can do with them. Now let's do the long answer. The long answer is, well, first let's take a look at the case where our polynomial p of z has only real roots. Let r be a root of p such that p of r equals 0, and just for the sake of this explanation, let's suppose that n is an even number, but it works just as well if n is an odd number. Then, if r is less than 0, p of r is equal to p of the negative square root of r squared, and then it's equal to 0. If r is bigger than 0, then p of r is equal to p of the positive square root of r squared, and it's equal to 0 again because p of r equals 0. Now down here I've said show that both of these substitutions result in the same polynomial equation about r squared. So let's let y equal r squared, just for the sake of convenience. Then p of negative square root of r squared is equal to p of negative square root of y, and then substituting that into our polynomial, we've said n is an even number just for convenience, changes nothing to the proof if n is odd. Alright, so then we've got p of negative square root of y is equal to a0, and then it's going to be minus a1 square root of y plus a2 square root of y squared, and then minus a3 square root of y cubed, and then it'll keep going on like this, plus dot dot dots, and then it would be minus a n minus 1 square root of y to the power of n minus 1, and then plus a n square root of y to the power of n, and this thing is equal to 0. And then from this point we can bring all the negatives to the other side of the equation. So that leaves us with a0 plus a2 square root of y squared would be just y, and then plus a4, and then we had square root of y to the power of 4, so that would be y squared, so on and so forth, all the way up to the last one, which would be a n, and then I guess it would be y to the power of n divided by 2. And then equals, on the other side we would have a1 square root of y plus a3, and then it would be square root of y cubed, which is the same as square root of y times y, plus a5, and then this time it would be square root of y times y squared, all the way up to a n minus 1, and it would be well, square root of y, run out of room here, square root of y times y to the power of n minus 2 divided by 2. And then let's just write out what we have here. So we have a0 plus a2 y plus, and then it goes all the way up to an y to the power of n divided by 2. And then this is equal to, and on the other side we can actually factor out square root of y here. And then we have a1 plus a3y plus a5 y squared, and then it goes all the way up to a n minus 1 times y to the power of n minus 2 divided by 2. And then from this point we would square both sides, Remember, since n is a even number, n divided by 2 is still a whole number. And then when we square this other side, the only part that isn't a whole number, the square root of y, would become y when it is squared. And so we would end up with a polynomial equation for which y, which is r squared, is a solution. So that was for the case if r was less than 0. Now for the case where r is bigger than 0, we don't really have to do anything different. All we have to do is observe that these negatives would go away and they would become positives. And then so when we brought everything to the other side down here, those would all be negatives, and so there would just be a negative square root of y that was factored out. But of course, when we square it, it doesn't matter whether the negative is there or not. So both of these substitutions, negative square root of r squared and square root of r squared, they both give us the same polynomial. And hence, it doesn't matter whether the root r was less than 0 or bigger than 0, r squared is still a solution of the polynomial equation that we get from squaring both sides of this blue equation here. Okay, so that situation we just considered the polynomial with only real roots, and so this substitution y equals r squared means that either r equals the positive square root of y or r equals the negative square root of y, and there are no other possibilities. Next we're going to look at the complex case. So what if our polynomial p has complex roots? So p of z equals 0 has complex roots. What do we do then? Well, the first exercise here is to show that if a plus ib squared equals x plus iy, then there's only two possibilities for a plus ib. So there's a fixed complex number c plus id, and a plus ib is the positive or the negative of that, and no other possibilities. So I'll leave that for you to work through. You can show that c is equal to this square root of a half times x plus the square root of x squared plus y squared, and d is equal to y divided by 2 times that thing. So yeah, because a plus ib is equal to the positive or negative of this fixed number here, there are only two solutions to this equation here, and one of them is just the negative of the other. And that's all we were really dealing with over here, just ignoring the idea of r being a real number for now. Just consider this thing as x. Then we have two cases. We have negative x or we have x. And we know that x squared is equal to y, which is the substitution that we are making here. And so all the working that we did, assuming that we had to have real roots, we don't really need that assumption. It works just as well with complex roots. And it's all to do with this step here when we square both sides, and the negative, which may or may not be there, goes away when we square both sides. So yeah, interestingly enough, by the previous slide, we can just make the substitution y equals z squared to get a polynomial with roots ri squared for all roots of p, where this time the roots r1 to rn can be complex numbers. They don't have to be real numbers. The working is exactly the same. And I got a little note down here, just that f of y equals square root of y for the complex numbers, or where the domain is the complex numbers rather. In this context, with the complex number domain, it doesn't mean the same kind of thing as it does for the real numbers greater than or equal to 0 as its domain. In this situation, we're just, well, if y equals c plus id squared, then the values that are returned by square root of y are plus or minus that thing. So we can get c plus id, or we can get negative c minus id. Both of these two things squared give us c plus id squared, whatever that is. So it's not actually considered a function here, it's just a mapping. It sends something to one or more other things. So yeah, just to summarize here, in case you hated all the other stuff and it was just a big confusing nightmare, let p of z equal the sum from k equals 0 to n of ak z to the power of k, and it has roots ri. Then to find the polynomial with roots ri squared, you can take the equation p of z equals 0 and bring all the odd powers of z to one side and all the even powers of z to the other. So let's just go ahead and do that. So a0 plus a 2z squared plus a to the 4 z to the 4. And again, let's just suppose that n is even this time. But it doesn't actually matter if n is even or odd. Everything will work just the same. So our last term will be an z to the power of n. And then on the other side, so yeah, we're setting this thing equal to 0. P of z equals 0. So then on the other side, we're going to have all the odd powers. So it's going to be minus a1z minus a3z cubed minus dot dot dot, and then minus an minus 1 z to the n minus 1. And of course, we can factor out that negative. So let's just continue down here. So a0 plus a2z squared plus an z to the n, and then that's going to be equal to the negative of a1z plus a3z cubed plus dot 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 plus an minus 1z to the n minus 1. Alright, and then if we square both sides, so we square this side and we square this side, then that negative is going to go away, because when you square it, it doesn't matter whether that negative is there or not. But more importantly, on this side, all the powers are even. So when we square everything, we're multiplying, or we're adding two even numbers together. For example, z to the power of 2 times z to the power of n is going to be z to the power of n plus 2, which is another even number. And on this side, all the powers are going to be even as well, because if you add an odd number plus an odd number, you also get an even number, because all these powers are odd. For example, z to the power of 1 times z to the power of 3 equals z to the power of 4. So you're going to get a big polynomial equation of order 2n, because z to the power of n squared equals z to the power of 2n. So you're going to get a big polynomial equation with order 2n, and all of the powers in that polynomial equation are going to be even. And so then you can go ahead and make your substitution y equals z squared, and that's going to give you a polynomial about y, and all of the roots, or all of the values ri squared will be roots of this polynomial about y. So basically the square root substitutions work because of algebra and the way polynomials are structured.